I would like to share with you the friendship theorem, which is a result in spectral graph theory proven by Erdős, Renyi, and Strauss in 1966. The friendship theorem, in its sociological form, is stated as follows. In a finite society with the property that any pair of persons has exactly one common friend, then there's one person who is everyone's friend. This one person who is everyone's friend is sometimes called the politician. To me, this is a highly unintuitive result on a first glance, even on a fifth glance, but it's indeed true. Now, this is sociology, but I said that this is a result in graph theory, and so I'll state the graph theoretic version. And the graph theoretic version is as follows. Suppose that G is a finite graph with a property that every two vertices have precisely one common neighbor, then there is a vertex which is adjacent to all other vertices. So a graph with such a property will look like this, and this is called a windmill graph. I'm going to call this a 4-windmill graph because it has 4, 1, 2, 3, 4 mills. You can have a 1-windmill graph, which is just a triangle, and so on. And we see that this graph has a property that any two pair of vertices have a common neighbor, and there is one vertex which is the common neighbor to, which is the neighbor to all the other vertices. So I did color it here in red. So for the proof of this theorem, the proof divides into two parts. First, we show that such a graph is a windmill graph, as I showed before, or is a regular graph. And the second thing is I show that such a regular graph that satisfies the conditions of the theorem is a triangle. And a triangle is not a counterexample because it is, in fact, a windmill graph. So to do the proof, we begin by making two observations. First, we observe that a 4-cycle is not a subgraph of G. Why isn't it? Because if I have a 4-cycle, okay, I pick two non-adjacent vertices. Well, in the 4-cycle, they have two common neighbors. Here's one, here's the other. And the conditions of the friendship theorem says that the common neighbor must be unique. So a 4-cycle cannot be a subgraph of a friendship graph. The second observation to make is that there is a path of length 2 between every pair of vertices. And that's, again, very easy to see. Pick two vertices. If they're not adjacent, then, or actually even if they are adjacent, then they have a common neighbor. And with this common neighbor, it forms a path of length 2. Okay. So to begin the proof of the first part, we show that any two non-adjacent vertices have the same degree. And this is just a counting argument. So we have U, let's say has some number of neighbors. Okay. We take a vertex, which is not one of its neighbors. By the friendship property, it has to join to one of the neighbors of U because U and V have a common neighbor. Okay, but this vertex has a common neighbor with U, again by the friendship property, and this vertex with V has a common neighbor with U, have a common neighbor. Okay. So now let's say V has some number of vertices, which are neighbors. Then a neighbor of U has to adjoin to one of the neighbors of V so that, for instance, this vertex and V have a common neighbor. And that is true with all of the neighbors of U. Notice, however, that a neighbor of U cannot have two common neighbors with V. The reason why is because, for example, here we formed a 4-cycle. And that is not allowed by the conditions of the friendship theorem. Likewise here, we have another 4 cycle. And so this edge cannot be here if this edge was already here. Okay. So now what we just showed is that the number of vertices of the number of neighbors of U is greater than or equal to the number of vertices of V. By symmetric argument, the number of neighbors of V is greater than the number of neighbors of U. And so they're equal. And, but maybe it's better through picture. I can draw the bijection between the vertices, the neighbors of U and the neighbors of V. Okay. So now we can show that G is either a regular graph, which means that every vertex has the same number of neighbors, or it's a windmill graph. The proof is as follows. Suppose G is not regular. Okay, then we can find two vertices with different degrees. So let's say it's U and V. Okay, U has some number of neighbors, V has some number of neighbors. Okay, but by the previous lemma, we know that U and V must be connected because they have different degrees. And they have a common neighbor W by the conditions of the friendship theorem. Now, let's take a neighbor of V, which is not a neighbor of U. Okay. This vertex and V must have a common neighbor. Let's say it's U. Well, that's a problem because now we've just formed a 4 cycle. So it can't be there. Likewise, it cannot be W because here, as we see, we have formed a 4 cycle. Okay, and this is true if we have an edge connecting any neighbor of U to a vertex of to this vertex, will form a 4 cycle, violating the conditions of the friendship theorem. And so this vertex can't be there because now it's impossible for it to have a common neighbor with V. So it's not there. Now, the neighbors of U have a common neighbor with U. So we can maybe draw them in. Okay, but notice the common neighbor cannot be V because we'll form a 4 cycle, and it cannot be W because we'll form a 4 cycle. Right here, it's a little hard to see, but if we go up to U, from U to W, down here, here, it's a 4 cycle. Okay, so those edges can't be there. And look what we just made. We ruled out all the other possibilities. What we're left with is a windmill graph. Okay. So now we know G is either regular or a windmill graph. So suppose G is K regular. The first thing I want to do is show that A squared, the adjacency matrix of A squared, is in this form. And this is really simple because the ijth entry of A squared counts the number of paths of length 2 between vertices I and J. Okay, so now let's do a counting argument. There are K paths of length 2 from vertex I to itself. You go out from the vertex and you go back in. You can do that K times because the vertex I has K neighbors. So that gives us the Ks along the diagonal. And by the conditions of the friendship theorem, there's only one unique path of length 2 from vertex I to J, but I is not J. Why is there only one unique path? Because if there were 2 unique paths, we'd have a 4 cycle. Now notice that this matrix can be written in the algebraically as Ki plus J minus I, where J is the all one matrix. Why is J the all one matrix? I'm not sure, but it is tradition in graph theory. Maybe someone can tell me. So now, from that algebraic expression, we're going to show that the eigenvalues of A are k with multiplicity 1, square root k minus 1 with multiplicity f, and minus square root k minus 1 with multiplicity g. This is also notation. We're writing the multiplicity of an eigenvalue as an exponent. I'm not going to change things. So first, we observe that k is an eigenvalue of the adjacency matrix of A because it is 1 regular, so it is k regular. So now, if we have any other eigenvalue, let's call it lambda, with corresponding eigenvector x, this eigenvector x is orthogonal to j. Okay. So now, if we can write it out, a squared times x is equal to lambda squared x, because lambda is an eigenvalue of a and x is the eigenvector. But we can rewrite a squared as ki plus j minus I. And because j is orthogonal to x, the rows of j dot producted with the vector x, which is what happened when we expand this matrix multiplication, is 0. And so we get k minus, this equation is equal to k minus 1 times x. And we conclude that lambda is equal to plus or minus square root k minus 1. And these have certain multiplicities, f and g I chose, but we know that f plus g is equal to n minus 1 because it must sum to the remaining subspace. Dimension of the subspace. We remove the eigenspace corresponding to eigenvalue k. So now we're going to show k is 2. And pretty clearly, if G is 2 regular, it must be a triangle. That satisfies the conditions of the friendship theorem. So let's prove it. The trace of A is 0 because it's an adjacency matrix with, and the graph is simple, it has no self-loops. I mean, I guess we're all friends with ourselves, but for this purposes, we don't count ourselves as our friend. So because the trace of a matrix is the sum of its eigenvalues, we get that k with multiplicity 1 plus square root k minus 1 with multiplicity f plus minus square root k minus 1 with multiplicity g. These sum to 0. So rewriting, we get that g minus f is equal to k divided by square root k minus 1. Now, g minus f must be an integer because g is an integer and f is an integer. It is the dimension of corresponding eigenspaces. With that information, we know that k minus 1 is a square number. And because g minus f is an integer, and because it's square, this s must divide k. Okay. From there, we conclude that the only such s with this property is 1. And so, plugging in 1 back in this equation, we get that k is 2. And we're done. G is regular, then it's triangle, which is a windmill graph. That's not a contradiction. That's it. And I hope you enjoyed that